Okay, well, first of all, thank you, Nicholas, for organizing this workshop and for inviting me. And thank you for everybody for staying here until the last lecture, the last talk. So I know you are tired, but so let me talk about this. This is a little bit, it's a long title, right? So let me explain what it means, because maybe you're not familiar with this terminology. So basically, this is about, so whenever you want to process information, basically you collect the observations in a big matrix, right? And then you do whatever you have to do, right? The problem is that in many applications, there are always some missing values in that matrix. And then whatever algorithm you are going to use later, it's not going to work when you have these missing values. So this is a big problem in practice, right? So imputation refers to dealing with those missing values, basically filling them in somehow. That's what it means, right? And in particular, I will talk about imputation for time series. My motivation comes from finance, so it's financial time series. And another important thing is that usually people assume Gaussian distributions because Gaussian is easy to deal with, but in finance you cannot assume Gaussian. So that's why we deal with heavy-tailed distributions. Okay, so that's the description of the title. Okay, so let me start with the motivation. Again, I already explained the motivation, right? Sometimes we have missing values and then nothing is going to work, so we need to do something about that. So, and this is a practical thing, right? Sometimes values are not measured for some reason. Sometimes they are measured, but they get lost, or there is some corruption on the storage. And sometimes they are measured, but they are wrong somehow. They could be an outlier or something. So there are many applications where you have these missing values. Many applications. In my particular case, the motivation comes from finance, and this is true. Actually, I remember 3 years ago downloading, stock data from Yahoo Finance, and I realized that every now and then you would find a missing value, and so that's how I got into this. So indeed, sometimes some stocks they are not traded some days. Different countries have different holidays, or maybe some stock is illiquid and it is not traded, or it is traded, but maybe the data that you have is not of good quality. It depends how much you pay for the data, right? So if you get the data from a Bloomberg terminal, probably you will get less missing values. But there are many other applications, like if you have sensors that they are measuring something, sometimes they may fail to measure something. Maybe the battery fails at some point, whatever. Another important application is when people do surveys, right? They design some survey, they give it to the people, and sometimes the people, when they answer the question, sometimes they skip some questions. And then you collect these, you go back to the lab, and then you realize you have missing values. What do you do? So one option is to throw away the samples with missing values, but if you do that, at the end you're going to end up throwing away a lot of useful information. So that's the idea. So yeah, that's what I was explaining. Now, of course, you cannot do magic, right? I mean, how can you fill in the missing values? You cannot do magic. So basically, the idea is that we want to fill in those values based on some properties of the data. There has to be something there, some structure that you need to know that, right? Otherwise, you cannot do magic. So in particular, in our case here today, I'm going to use the fact that time series, usually they have some structure along the time domain, right? So that's going to be our structure that we're going to use to do the filling. And then, yeah. So, but anyway, there are many imputation schemes. This is a very old topic. Some imputation methods are totally heuristic, ad hoc, and some of them they are totally wrong. It's better even not to do it than to do it sometimes if you do it that bad. But we want to do it in a sound way, a statistical way, right? We want to do it in a way that if you fill in the missing values, you don't destroy the statistics of the original time series. That's the idea. And as I said, many works assume Gaussian. We cannot do that here. So this is the focus of this presentation, okay? Statistically sound methods for time series imputation and the heavy tail distributions. Okay, let me tell you, just for fun, this is a very common example of imputation. It's totally different from our topic today, but just for fun. This is a Netflix problem that started many years ago, I think 15 years ago or something. Basically, the idea is that Netflix, they had this big matrix, right, with the rating by different users on different movies. Right? If a user watches a movie, then it will give a rating from 1 to 5. But of course, as you can imagine, most users, I mean, a given user has not watched most of the movies, right? So basically, this matrix is going to be pretty much empty. It's going to be full of missing values. So the problem in Netflix, they wanted to recommend movies to the users. So somehow they wanted to fill in those missing values so that if they fill in a value and there is a 5, they can recommend that movie to you. But how do they do that? Well, in this case, of course, you cannot do magic. So in this case, there was some structure that they exploited. And we are not going to get into the details, but the structure is that you can argue that this huge matrix is actually low rank. That was the trick. So basically, you can write this matrix as the product of two very thin matrices. So that was the trick. Once you realize that it's low rank, you can actually fill in the missing values. So they had a competition actually years ago, right? And the winning method basically was this, combined with many other things, right? Anyway, this is just for fun. Now, in our case, we are going to use the structure along the time domain. It's totally different from the low rank structure. It's a different thing. So basically, the idea is that, well, YT is the time series, and there is some structure. In this case, it's a random walk. So YT is equal to YT minus 1 plus some innovation. So there is clearly some structure. There are many other models, like AR model, right? In an AR model, well, YT depends on the past few values plus some random innovation as well, right? So clearly, if one of these guys is missing, you know, you can have a good guess on how to fill in, right? So that's the idea. So let me tell you a little bit about different imputation methods. Just hot deck imputation is like one of the oldest methods. Basically, what they do is just basically, if there is a missing value, they take some other value around and they put it there. That's it, right? Well, of course, in some applications maybe it works, but in some others it could be really bad. Mean imputation is something that sounds very natural. Imagine you have a time series, right? And there are a few missing values. So you could do the following. You look at the observed values, you take the mean, and you put the mean in the missing values. It sounds totally reasonable, right? Yeah, it sounds like a good idea, but it's really bad because it distorts all the statistics of the signal. And I can show you, it's very easy once you realize. So imagine we have K1 observations and K2 missing values, NA, not available. This means not available, okay? So K1 observed and K2, they are missing. Well, of course, if I want to compute the variance of these numbers, I will just discard the missing values. Of course, they are missing. And I will just take the ones that I know. I'm assuming here IID, I guess. So I would take the K1 values and I estimate my variance, 1 over K1, summation of all these K1 observed values. That's my estimation. Okay, good. But imagine now we impute with the mean and then we compute the variance. So now, where we had missing values, now I put the mu. Once I impute this mean, I'm going to estimate the variance, forgetting that I imputed, right? Well, look what happens now, because I don't throw away these guys. Now I have K1 plus K2 numbers. So my estimation is going to be 1 over K1 plus K2. And this summation is for the first samples. And this summation, of course, that's the problem, right? That the summation corresponding to these terms is just 0. So basically, at the end, this summation is the same as this, but this one is divided by K1, and this one is divided by K1 plus K2. So it's totally distorted. It's going to be underestimated. So you see, it's very dangerous. You can easily make mistakes when you do imputations. So this is really bad. It sounds like a good idea, but it's bad. So basically, all these interpolations tricks that you can think of, maybe they work for some applications, but that's not what we are looking for, because they are not statistically good. And I'm going to show you a plot. Look at this. Basically, I took some probably the SP500, some index, and I plot here the price over time, right? And then what I did is I removed a block of prices, and I imputed according to different methods. This is a very popular imputation method. It's called LOCF, last observation carried forward. Basically, I just repeat the last observation, bam, 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 until I have more observations. So there is a big jump. It looks quite horrible, but in finance they use that all the time, by the way. So here you could say, okay, let me do something better, some linear interpolation. But you can see it's totally fake. I mean, all this is fake. Here you can say, okay, let me use some spline. Still, it's fake, right? It's fake, and it destroys the statistical information. So this is what we are looking for. If you look at this looks natural, right? That's what we want, okay? That's the idea. So let's try to do that. Let's try to do that. So in order to do a proper statistical imputation, we can think of two steps. The first step is to actually characterize, the statistical properties of the time series. Okay, estimate the parameters of the PDF or whatever. Right? Characterize it. Once you characterize it, then you can do the imputation. But the first step is to characterize it. So let's do the first step, which is the most difficult. Actually, once you characterize the time series, the imputation is easy. So this is the difficult part. Okay, so let's start from a simple example, and then we make it more complicated. Simple example. Let's assume we have IID, observations, and Gaussian. It cannot be easier than this, right? So what do you do? Well, basically, we want to, a Gaussian distribution is characterized by the mean and the variance. So we want to, estimate the mean and the variance. We're going to use maximum likelihood, a very common way of estimating parameters. The idea is that you evaluate the PDF of the Gaussian on the observations that you have. In this case, they are IID, so we multiply all these, and then we take the log, and that's the likelihood. And then you want to maximize this with respect to mu and sigma. Okay, that's maximum likelihood. But now we have missing values. But because it's IID, basically what we're going to do is throw away the missing values and just keep the observed ones. That's it. That's going to be the maximum likelihood. So you see, here actually I only multiply the PDF evaluated in the observations that we have, not the ones that we don't have. So it's nothing new. Basically we just use the observed ones. That's it. Not only that, this maximization has a nice closed form solution, which basically is the sample mean and the sample variance estimator. But of course, you are only using the observations, the observed ones, okay? Okay, very nice. That's the Gaussian case, IID. But as I said before, in many applications, Gaussian distribution is not satisfied, in many big data and finance applications. So we are going to assume a heavy-tailed distribution, okay? And in finance, for example, it is totally true. In finance, if you take I take some prices of some stock, I compute the returns, and I plot the histogram. And then this blue line is, I'm trying to fit with the blue line a Gaussian. It doesn't fit at all. Basically, you see the Gaussian the tails quickly go to 0. But actually, the real distribution has heavy tails. That's why it's called heavy tails, because the tails are very heavy. They decay very slowly. Okay. So anyway, that happens in many applications, also in big data. Yes, sure.
So I work with missing data a lot. My advisor actually is raw label. The bulk that you sign, you reference.
Oh, okay.
So I'm raw so I work missing data actually is part of my dissertation. So maybe you could help me to, because I don't work with financial data. I like, for example, you're talking about the stock price on Google, whatever. You only have one-time series. Like, I assume that the missing data you have are not like missing, not at random. like either it's missing complete at random or missing at random.
Well,
So
yeah.
what's the point of doing imputation? You can just ignore. You don't have to model missingness at all.
Okay, yeah. Let me hold this question for 2 more slides,
Okay.
because in the IID case, you're right. In the IID case, if you have something missing, don't use it, and that's it. The problem is when there is some temporal structure, then you cannot just throw away things, because if you throw away things,
No, I don't throw away things. I mean, you still use the available data points, and you just don't have to model that part. Like even without.
I understand.
Even without imputation, you can still work with.
Definitely. The processing that you do later, if you are smart enough and you can design whatever processing you do to take into account missing data somehow properly, then yes, you don't need to impute. Yes. But the point is that we don't want to be, maybe we don't want to design all the algorithms in a complicated way to take into account that some values are missing. So imputation is just to impute so that you don't need to worry about that.
You impute the data already doing some complicated things. I mean, you are modeling your time series and you try to estimate parameter, given the parameter, you're going to impute the data. And that somehow already.
So, okay. Yes. So if you are going to estimate the covariance matrix, if that's all you're going to do, then yes, you can actually estimate a covariance matrix taking into account the missing values, and you will use some EM. Yes, you can do that. But maybe you are doing some other processing later. Maybe not only estimation of the covariance matrix. Who knows what you are going to do with the data later. So the imputation allows you to, solve that problem of the missing data, and then it's clean, and then you pass it to the next stage. But definitely, if you can take into account missing values already, yes, then do it. Yes. And in fact, yeah, we also do these things for estimation of covariance matrices. Definitely, you can do that.
Like the benefit compared to other cases where, like for example, clinical trials or you do surveys, right? So the government released the data for public use. I mean, they fill in the data. People like from everywhere they can download the data and use it. I mean, there's a big benefit of making the data complete. But in your case, I don't see the benefits. I mean, maybe there's benefits.
As I said, it depends on what you do later.
It's small.
If you are just going to estimate the covariance matrix and you can deal with missing values, fine, do it. But depending what you do later, maybe you didn't design the method to deal with missing values. You were not thinking about that when you design whatever method. So this allows you to still be able to use that method. So basically you separate into 2 stages. First impute and then do whatever you do. But if you want to do it together, that's fine. Okay, so yes, we were talking about the Gaussian case, and now let's do it with the student, with a heavy tail case, but still IID. So in this case, we need to use some heavy tail distribution, right? There are many heavy tail distributions. Which one you choose is not really that important in practice. The important thing is that you use a heavy tail one. So in particular, we use the student T, which is a family of heavy tail distributions. They have one more parameter to control how heavy the tail is. So in this case, you can see not only we have the mu and the sigma, but also the nu. The nu tells you how heavy it is. And in fact, if nu goes to infinity, it becomes Gaussian. Okay, so how do we do here? The estimation of the parameters. Again, let's do maximum likelihood, the same we did before. So basically, it's IID, so you can throw away the missing values. So basically, you just take into account the observed ones. You write this PDF, you evaluate the PDF in the observed values, take the log, and maximize. Fine. Fine, except that this doesn't have a closed form solution. So that's the first difficulty that you encounter with heavy tail. Okay, then what do you do? Well, there are different things you can do, but one way is to realize that the student T can be expressed in a hierarchical way. You can include some hidden variables that have a nice distribution, and then condition on the hidden variables. It turns out that this student T is just a Gaussian. So once you realize of that, you can say, okay, let me use this hierarchical description instead of this one. And you can do that, but of course then you need to deal with these hidden variables, and the way to do that is with the EM algorithm. You can use EM to deal with that. If we do that, we are going to be able to get a closed form solution. So anyway, we do that. It gets nasty, right? You need to do all the mathematical development, because basically what EM is going to do, let me go back. What EM is an iterative method. I guess everybody probably knows EM, but it's an iterative method. At each iteration, you do two steps. One step is expectation. It's called expectation step. Basically, you're going to approximate this by another function. And in the second step, you maximize the approximation. And then you do that iteratively. So this is the first step, expectation. Basically, this Q function is the approximating function. And basically, you take the log of the complete PDF, right? But you need to take expected value. That gets complicated, okay? Expected value of the hidden variables, condition on the observed ones. So it gets nasty. So, but anyway, you do it, and at the end, well, you can get an expression that is clean. And now you need to maximize this guy with respect to the parameters. Luckily, it can be done in closed form. Good, thanks to the EM. Yeah, forget the details, that doesn't matter. The maximization of that Q function, nice, closed form solution. And you can write it, pam, pam, pam. And actually, mu is like a sample mean, but with some weights. And this sigma is also like a sample estimation, but with some weights. So it's kind of nice. Fine. So this is just to warm up. Now let's do the thing that we really want to do. The thing that we really want to do is forget about the IID. That complicates things. Let's assume, for the sake of simplicity, that we have an AR1 model. So basically, it's something like that, right? Now you can see each sample is somehow related to the previous one and also affects the next one. So you cannot just throw away things, because things are connected. So now it's going to get complicated. So okay, let's try. By the way, now the parameters we want to estimate, we have 4. Now we have this psi 0, psi 1, and then the variance of the innovation, and also the how heavy the tail is of the innovation. Okay, so we have 4 parameters, but that's fine. Let's do the maximum likelihood formulation now. Let's see what happens. Well, what happens is that we write the PDF, we evaluate the PDF in the observed values, but there are some other values that are missing. How do you deal with that? You actually need to integrate them out. The missing ones, you need to integrate them because you don't have them. So you need to integrate them. And then you take the log and maximize. Now the problem is even worse than before, because before in the IID HeavyTailed case, at least we could write this expression. The problem was that we couldn't maximize it in closed form. But now the problem is that we cannot even write this. This integral, you cannot write it in closed form. So you don't have a closed form expression to maximize. So it's really nasty. Then you say, okay, let's see if I can do this hierarchical decomposition, and let's see if that helps. But now it gets more complicated, because now the hidden variables are going to be not only these taus, but also the missing values. They are going to be also hidden variables. Fine. So then it gets complicated, right? It gets complicated, but you try to do EM. Okay, you write the PDF. At the end, you can write it in a nice way. And the difficult part is this, right? When you want to compute the Q function, basically you need to compute this expected value. You try to do it. You manipulate things. And at the end, the only thing you need to compute at the end is this guy. That's the only thing we need to do. Expected value of this vector, that this is a vector of the sufficient statistics. The problem is that it cannot be done in closed form. Even this simple expected value, it cannot be done in closed form. So we are a bit stuck here. Then, well, but there are ways to do it. There is something called stochastic EM. Basically, in the stochastic EM, what you're going to do is you're going to approximate the expected value. Instead of doing analytically, what you're going to do is you're going to do it like numerically, basically. You're going to generate realizations of this conditional distribution, and then you're going to take like a sample mean. Okay, but you need to generate randomly from this distribution. Fine. The problem is that even that you cannot do. Okay, if you write it down, you cannot generate random realizations of this distribution. Okay, so but anyway, there are techniques to do it. So yeah, that's what I'm saying. We cannot even generate realizations of this distribution. But there are some techniques, right? Markov chain Monte Carlo methods. Basically, in particular, we use here the Gibbs sampling method. So the idea is that instead of generating jointly all the hidden variables, which are in this case the taus and the missing values, instead of generating jointly those guys, which we don't know how to do, we're gonna use the Gibbs sampling, and what it does, the Gibbs sampling, is it generates only one of them, condition on the other ones, fix on the other one, you generate this, and then you fix this and you generate tau. But of course, if you do that, it's not the same as generating them jointly. If you generate one marginal, the other marginal, that's not the same as generating them jointly, right? But basically, what the Gibbs sampling method does is it generates this alternating thing for a long time until it converges. And once it converges, what you are generating is like the joint distribution. Okay? Anyway, nothing new. This is Gibbs sampling. You need to do it properly so that it works, and in this case, it can be done properly. So at the end, the only thing we need to do is to draw the tau, given all the y's, and this is trivial because the tau is just a gamma distribution. And then, given the gamma and the observations, draw the missing. Again, this is trivial because this is just Gaussian. So basically, we draw this, pam, 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 until it converges, and then that's it. That's going to give us one realization of the joint. Good, so that's it. That's the stochastic EM applied here. It can be done, and it works very well. So at the end, it's three methods, right? You need to simulate these joint things using the Gibbs sampling, and then you approximate. This is when you approximate the expected value with this summation. And then the maximization step. I'm not going to give you the maximization step, but you can compute it in closed form. It's very nasty, but it can be computed in closed form. So that's it. So once we have characterized the PDF, right? Once we have characterized all these parameters, we can do the imputation. How do you do the imputation? Well, basically, we have characterized this. So once we have characterized this, we can just draw the missing values from this, and that gives us one imputation. And if you want multiple imputations, you can do this several times, and then you get multiple imputations. Okay, so that's it. That's it. I want to show you some numerical results. Basically, here I took some real data, SP500, and I'm trying to fit it with the example that we saw, right? A student T, AR1. Okay, so we have 4 parameters, right? So indeed, if you do this procedure, it converges very quickly, pretty much 40 iterations, everything has converged. Basically, oh, by the way, we know already that the log prices, they follow a random walk. So actually, the psi1 in the AR model, we know that it should be a 1. Indeed, phi1 is here, it quickly converges to something that is like 0.9988, so it's like 1, right? So fine, works fine. This is, everything converges. And the new converges to something around 5, so definitely heavy tail. 5 is still very heavy tail. So good that we are assuming a heavy tail. Good. And now let me show you one more plot that I think is quite interesting, okay? I want to test you, right? Look at this. So this is a real data, right, from the SP500, and I plot here, right? So we have, you can see 4 plots, right? Basically, I have what I have done here. I have removed some block and imputed. Can you recognize where is the imputation here? With the naked eye, can you see which part I imputed or not? It looks It looks very natural. Just to help you a little bit, I'm going to draw in a different color the part that I imputed. I don't know if you can see it. You see the blue? The blue is the part that I removed, and then I imputed, right? I imputed multiple times, right? So, does it look natural to you? One of them is the real one, by the way. One of them is the original one, and the other three are imputed. Anybody wants to guess? So who thinks this is a real one? Who thinks this is a real one? Nobody wants to say anything? Who thinks this is the real one? Yes? And who thinks this is the real one? Interesting. So the majority of the people think that this is a real one. Some people think this is a real one. Actually, this is a real one. So anyway, just to show that if you do it like this, statistically, you cannot tell the difference, right? Both visually, you cannot tell the difference, and mathematically, statistically, you cannot tell the difference because those imputations, satisfy the statistics of the original part of the data. Anyway, so that's it. This is, by the way, I come from HKUST in Hong Kong as well, on the other side of Hong Kong, basically. So this is where we are. So thank you very much.
I really enjoyed your talk. I'm a biologist, so I don't have a sophisticated question to ask. And so kind of from the standpoint of the general population, one thing I guess I would wonder is, does this mean it would be that much harder to figure out fake data from real data in some type of situation?
So, if can you say it again? If it would be...
Well, for example, with images, it's possible to tell whether an image is faked by certain statistical properties of the underlying data structure. And I'm curious here, I mean, probably people wouldn't be taking this type of financial data, but I'm wondering if this means that it would be relatively straightforward to generate fake data.
Oh, yeah. I think in finance it's very easy to fake data. Yeah. Basically, there are many models in finance, very complicated models to try to explain the data, right? Not just the AR1, right? Very complicated models. So you can take any of those models and put some parameters and generate the residuals randomly, and that's it. And you draw something. And if you choose meaningful parameters, then yeah.
But to fill in the data though, with the other models before the type of thing you're doing, would you have been able to recognize that the data really had been filled in?
Yeah, because they were not statistically consistent. Yeah. I think once you do it in a statistically consistent way, it's maybe some expert who spends every day looking at the charts can tell the difference, but yeah.
Like the way that you impute data actually based on the original data, you are not creating anything artificially wrong. Like unless like if, for example, if like the data are missing completely at random, basically you're filling in the missing data point just based on the original information. There's like no additional assumptions goes into the missing data imputation process. It's just like if the information is 100% and after imputation is still 100%, you are not getting like 120%. Like you are not creating new information at all, unless like the way the data is missing is not missing at random. Like the way the missing data actually different from the data you observe. In that case, you have to make some assumptions. Yeah.
But in this case, we are making some assumptions on the model. For example, here, right, I was making the assumption of AR1 model, which is good enough to fake it. But so you are making that assumption, the model that you use. Yeah.
Yeah, if the model is wrong, definitely. I mean, the data points that you impute actually look different, systematically different from the original data points, but you don't want the imputation model to be wrongly specified.
So another way to generate fake data is with deep learning, the adversary neural network, right? That's what they use for images. So in principle, you could use it also for any kind of application, yeah.